Okay. Good morning. Newton's laws of motion. There are three laws basically which govern Newton's this complete chapter, rather whole of mechanics. The first law defines mass. Indirectly, it is giving you a measure of inertia. Indirectly, it is giving you a measure of inertia. Right? Newton's laws of motion में the first law gives us a measure of inertia. For any change in state,
Yes, sir.
Yes, sir.
for any change in state, there should be an external force. For any change in state, there should be an external force. Body at rest will continue to be at rest. Body moving with uniform speed will continue to move with uniform speed unless and until there is an external force.
Yes.
Unless and until there is an external force. First, I'll dictate the statement, write down till here.
Sir, external unbalanced force.
Temporarily write external force. That will do. We will speak about unbalanced force in the second.
Okay, sir.
Write down the statement. Every body continues. Every body continues in a state of rest. Every body continues in a state of rest. Every body continues in a state of rest or a uniform state of motion. Or a uniform state of motion. Or a uniform state of motion. Unless compelled by an external force. Unless compelled by an external force. This is precisely first law. Every body continues in a state of rest or in a uniform state of motion unless and until compelled by an external force. Suppose I am at rest, I continue to be at rest. If there is an external force, I'll move. Suppose I'm moving with uniform speed, I should be continuously moving with uniform speed or velocity. What brings me to rest? External force called friction. External force called
Friction.
no external force, there is no change of state. What do you mean by change of state? Body at rest should be at rest. Body moving with uniform velocity will continue to move with uniform velocity. There must be an external force to change the state of the body.
Sure.
Yes.
First point, internal forces don't change the state of the body. Internal forces do not change the state of the body. Sitting inside a car, you can never push the car.
Yes, sir.
Yes, sir.
Inside a car, you can never push the car. You get down and you push, it will move. At most, you will push the front seat off, but the car
Yes,
will
sir.
not move.
Yes, sir.
Now, then sitting inside a car, you drive the car, no yaar. Sitting inside a car, when you drive the car, your engine can make the wheel rotate. That's all. Your engine doesn't make your vehicle rotate. All that your engine does is, it makes the wheel rotate this way, clockwise. So this point will slip in the backward direction. Velocity of this point is in the backward direction. Friction opposes relative motion. So their friction is acting in the forward direction, which will make your vehicle go in the forward direction.
Yes.
What makes my vehicle go in the forward direction or backward direction? It's friction. All that your engine can do is make the wheel rotate. All that your engine can do is make the wheel rotate. The point will slip in the backward direction, friction opposes. You mean to say if there is no friction, vehicle will not move, it will not move. Friction is the main cause, the external force which makes your vehicle either move or bring it to rest. On a smooth, frictionless ice pond, you must be James Bond to drive your car.
Okay.
Sir, James Bond has
Yes, sir.
Smooth,
We are not able to
frictionless
walk also on
ice
that.
pond. You must be James Bond to drive a car. You need friction. A famous tire manufacturing company says, your brakes stop your wheels, our tires stop your vehicle. They are right. That's why tires have grooves. It is the friction which is making your vehicle move or bringing it to rest. This is the way your vehicle moves. Vehicle move. How will it come to rest? Your brakes will stop the rotation of the vehicle. Now your vehicle is moving this way. When you apply brakes, it prevents the wheel from rotating. Once the rotation stops, the vehicle will be skidding. Now this point is slipping in the forward direction. Velocity will be this way. Friction will act in the backward direction to stop the vehicle.
Yes.
Both the cases, it is an external force which either brings your vehicle to rest or it makes it accelerate. Without an external force, change of state is not possible. Without an external force, change of state is not possible. Is this point clear till here?
Yes, sir.
Yes, sir.
Take it down.
So the brake also applies a force only, right? Like to stop the wheels, and then friction they acts, so your vehicle stops.
आप बोलना क्या चाहते हो?
So I'm just asking you if what I said is
Drop
correct.
your mic and take it down.
Sir, if internal forces don't change the state of the body, we can consider each and every object as a particle. Say, in a question, we are given a car is moving with the speed, so we can consider the car also as a particle. If internal forces.
As on date, till we come to rotational dynamics, this topic in all Russian textbooks will be referred to as particle dynamics. Till we come to rotational dynamics. This rotation we don't define till we come till the chapter. For us, every body is a point object. This chapters will also be referred to as particle dynamics. Every body will be considered to be a point object.
Okay, sir.
To define the second law, we need another physical quantity. Second law. We define a quantity called momentum. Momentum is defined as mass into velocity. It is a vector quantity mv. Momentum will be written as mv. What will be the units of this? Kg meter per second. Mass is kg, velocity is meter per second. Right? Kg meter per second. Momentum is a physical quantity which is a vector quantity. Newton's second law statement goes this way. External force applied is directly proportional to rate of change of momentum. Newton's second law statement is 1 second, wait.
Addressing DD.
Here, external force will be equal to rate of change of momentum. You write this as dp by dt. F external is the rate of change of momentum, right? D by dt of mv, F external. Now this will be m dv by dt. Very technically, this should be u into v. Then why are you not putting dm by dt? We will in the chapter conservation of momentum. Till then, for me, the mass is constant. Till when mass is constant, I will skip this part of this will be 0. Till when mass is constant for me. So F external will be equal to m into a. This is precisely Newton's second law. Right? This is precisely Newton's second law. F external is mass into acceleration. But then this is half the truth. The remaining half of the truth we will deal with in conservation of momentum, where mass will be varied. Till then we will take particle objects or point objects, where the mass will remain constant. Hence dm by dt is 0. Take it down till here. Proportionality, I put it as 1. Rate of change of momentum, the proportionality constant is 1. There are a few spammers in today's class, hence I have put you people on mute. I have no other option. For second law, I did not dictate a statement. This is the statement. External force applied is directly proportional to the rate of change of momentum. In this case, proportionality constant becomes 1, not always. I will address every possible issue that comes to my mind. Don't trouble yourself with unnecessary doubts today, right? And this must be an external force. Internal forces do not change the momentum of the system. Individual particles can change. My one hand can fly this way. Momentum of every point change, right? There is an external force on me, friction. If not, I would have moved in the backward direction. Now there is a third law. Third law. Every action has an equal and opposite reaction. Write down the statement. Every action has an equal and opposite reaction. Every action has an equal and opposite reaction. Every action has an equal and opposite reaction. Underneath that, write a note. Underneath that, write a note. Action and reaction are never on the same body. Action and reaction are never on the same body. Action and reaction are never on the same body. If standing here I throw the marker, I'll get back an equal and opposite reaction. I'll be pushed in the backward direction. Standing here I throw a marker, I'll be pushed in the backward direction. Then why am I not moving? There is friction between my feet and the ground. If there were no friction, I would be set into motion in the backward direction. Have a look at this example given by Halliday. He is asking in one of the reasoning questions, if you are standing on a large ice pond, frictionless, smooth surface, propose a way in which you can come out of it. You cannot walk because it is smooth surface. On a smooth surface, you actually walk by pushing the ground in the backward direction. You get back a reaction because of which you go in the forward direction. I will push the ground in the backward direction. By pushing the ground in the backward direction, I get back an equal and opposite reaction. Now on a perfect smooth surface, I cannot push. I don't get reaction. I will remain at the same place. So what is the other alternative? Throw anything that you have got with you. Maybe a marker, maybe a shirt, maybe a t-shirt. Even if you spit, the saliva gets the action, your body gets the reaction. It may be very small, no, yeah, doesn't matter. You will be set into motion with lesser acceleration. We are perfectly okay with the value of lesser acceleration, but you are set into motion. You will thereafter be moving with uniform speed or velocity till you reach a point where there is friction. You cannot sleep and slide. You need friction for sliding. You will remain at the same place till you have an external force. Sneeze, you will be pushed in the backward direction. Spit, take anything in your pocket, throw, you get back an equal and opposite reaction. Action and reaction will never be on the same body. You can never tell me this is action, this is reaction. If this is action, this is reaction, the body will never move. Such a thing is wrong. Action and reaction will never be on the same body. I am pulling the body will pull me. Somebody is typing hop. How will you hop and where will you hop? You will be hopping at the same place. You will not get a horizontal force by hopping. Walking and hopping, there is no difference. You are using only one leg, that is hopping. You are using two legs, it is walking. Both are the same for me as far as physics is concerned. Right? Ice skaters, they push the ice with the two sticks that they hold. They push, they prick and push. If you see a Russian ballet, two people will perform this Russian ballet. Their shoes will have a knife edge. It will dig into the ice and it will use the groove. Every place you need an external force. If not, you will not be able to move. Action and reaction are never on same body. Action and reaction are never on same body. Right? Make a note of it and put a cross. This free body diagram will be wrong. This will be wrong. Put a cross here. Do not fail in that. Several times we see students committing this mistake. It's more like telling you, place Mount Everest on a frictionless surface. I will move it with a single finger. Place Mount Everest on a frictionless surface. I will move it with a single finger. Conditions apply. I should stand on a surface with friction. I should stand on a surface with friction. If not, I will be flying back with equal momentum. Place Mount Everest on a frictionless surface. Smooth. I will move it with a single finger. Conditions apply. I should stand on a surface with friction. If not, I will be flying back with equal momentum. All of you stop typing unnecessary messages. Per second, 20 messages. Unnecessary. Unless there is something very serious to discuss, don't type. Now, in this chapter, we will deal with two types of forces. I will pull using a string. The name of the force will be tension. You will pull using a string. The name of the force will be tension. You will push using any body. Name of the force will be normal force. In this chapter, we will deal with these two forces only. In one case, I will pull. Using a string, I can never push. Using a string, I can only pull. I cannot push. I want to push this block. I can pull this block. I can pull this block up. I can pull it on a surface. I can pull this on a surface. I am pulling it. I cannot push. String is basically used to pull a body. You cannot push. Right? Two things that we will speak of. First, we will speak about the string and tension. We will deal with this force first of all. Spring we will come to later. Right now, spring will come after we are done with this. Right now, string. In our language, when we speak about a string, we are considering inextensible string. What do you mean by inextensible string? Inextensible string means length will be constant. Length is constant. It doesn't stretch. Inextensible string means length will be constant. Right? Second assumption that we take in this chapter is massless string. If the string doesn't have mass, tension is the same all throughout the string. All throughout the string. Tension is the same all throughout the string at different points. If the string is inextensible, its length will remain constant. It doesn't stretch. If the string is of negligible mass, tension all throughout the string at different points will be the same. Third point. Tension acts away from a point with respect to the point. Tension acts away from a point with respect to the point. Tension always acts away from a point with respect to that point. Keep this in mind. I'll explain this in detail. Take down all the 3 points. Tension acts away from a point with respect to the point will be explained. Take it down till here. 2 types of forces in this chapter. 2 types of forces in this chapter. Now, why will the tension change if the string has mass? We will come to it a later stage. We will go to that step by step. There will be a day when you take mass for the string as well. No. Listen to this. There are two people standing. Both of them are pulling the string. I am pulling the string. String should pull me. Why? Newton's third law. Every action has an equal and opposite reaction. I am pulling the string. String will pull me. So string is pulling me. Tension will act away from the point with respect to the point. With respect to me, the string is pulling me. Same applies for this man. This man is pulling the string. String will pull him. Every action has an equal and opposite reaction. This man is pulling the string. String will pull him. This man is pulling the string. String will pull him. Action and reaction. I am pulling the string this way. String is pulling me in the opposite direction. I'll give you one more example. Have a look at it. This is a ceiling, this is a string, and this is a load hanging down. Who is balancing the weight of this load? mg is acting in the downward direction. Somebody is balancing it. The load is not falling. Fan is not falling down. It's hanging there. Who is balancing the weight of that? This tension is balancing the weight of that. This is the way you draw the free body diagram. Tension in the string is balancing the weight. Tension is acting away from the mass with respect to the mass. With respect to this mass, it acts away from the mass. Second, the string is massless. So tension will be the same all throughout. With respect to the ceiling, tension will be in the downward direction. With respect to the mass, tension is in the upward direction. Away from the point with respect to the point. Away from the point with respect to the point. If you people observe, if there is a rope tied to the ceiling and I pull, on the ceiling, the force is in the downward direction. If you people observe, there is a rope tied to the ceiling and I am pulling the rope. On the ceiling, the force is in downward direction. The force is in downward direction. Tension always acts away from a point with respect to that point. Tension always acts away from a point with respect to the point. String cannot push. If there is a string and I am pulling, do you think the string will push the ceiling in the upward direction? If there is a string and I am pulling, will the string push the ceiling in the upward direction? It will pull the ceiling in the downward direction. So on the ceiling, the tension is in the downward direction, away from a point with respect to the point. Saumil Shah is typing action and reaction are on the same body. Action is on the string, reaction is on the man. This is action, reaction. This is the tension on the man, right? Man is pulling, string is pulling him. That is action and reaction. These two are not action, reaction phase. These two are not action, reaction phase. Man is pulling in this direction. Tension is pulling him in opposite direction, right? Gaurav Kabra, for God's sake, can you stop typing messages unnecessarily? Now you want me to explain what if it is a rigid rod. Pehle string khatam kare ya chhod de? Chhod do string and go to the rod. Keep your ideas to yourself and wait for some time till I come there. I cannot keep jumping over topics. Stop typing unnecessary messages. Now that is the last means of communication you people can have with me. I close that as well. You will not have any means of communication. So when I am teaching about tension, can you learn about tension, or is it so that you will have to learn about normal? टेंशन तो सीख लो, और अगर आपने सीख लिया, keep share. Is that clear? Now, somebody is speaking about the center. At the center, every time it is with respect to one particular point. Forces will not cancel out at the center. Tension will act here at this particular point and this particular point. I will show you how by drawing the free body diagram. First, to take this down. Mg and T are not action-reaction pairs. Mg and T are not, they're two different forces. Incidentally, here tension turns out to be equal to Mg because the block is at rest. No. Right. Have a look at one more example. I will take a numerical example to explain this. This is a 10 kg block. This is a 5 kg block. Very elementary things. I'm going very slow because I assume everything is a doubt and I'll answer it. Right? Please concentrate. Firstly, if it is one string, tension will be the same all throughout. If there are two different strings, tension need not be the same. I have one string here and one string here. Tension in this and this need not be the same, but all throughout this string tension will be the same. We call something as a free body diagram. First, we separate the body and draw the forces acting on it. 10G is one force. With respect to this, tension will be in upward direction. With respect to the 5 kg plot, tension will be in the downward direction. Away from a point with respect to the point. Away from a point with respect to the point. Away from a point with respect to the point. Now, here I will take tension to be T2. This tension will be T2. All throughout this string, tension will be the same. But with respect to the ceiling, tension is in the downward direction. With respect to this block, tension is in upward direction. Now draw the free body diagram for this. This is T1 and this is 10G. This is 5G plus T1 and this will be T. Every force acting on them is shown. On the 5 kg block, T2 is in the upward direction, T1 is in the downward direction, 5G is in the downward direction. And the body is in equilibrium. Body is in equilibrium implies T2 is 5G plus T1. T1 is 10G. This is my first equation. This is my second equation. Body is not accelerating. So forces in upward direction will be equal to forces in downward direction. Same applies here. Forces in upward direction will be equal to forces in downward direction. What you need to catch is the way I have taken tension in the string away from a point with respect to that point. 5 kg block will be pulled in the downward direction by this, will be pulled in the upward direction by this. For the ceiling, T2 will be in the downward direction. I didn't write the dynamic equation for the ceiling. Equilibrium means acceleration is 0. Equilibrium means acceleration is 0. Now substitute this T1 here. T2 is 5g plus 10g. This is 15g. I got T2. T1 is already got as 10g Newton. 15g Newton. Units of force is Newton. Units of force is Newton. Take it down till here. I'll give you one problem which you will solve on your own. Somebody is worried about direction of tension at the center of a string. If two people are pulling, please listen at this stage. This is unnecessary, but this will keep eating your mind. Take a particular point. With respect to this point, tension will be this way and this way. Always away from a point with respect to the point. Away from a point with respect to the point, wherever you be. With respect to this man, tension is away. Tension is away. It always pulls. It always pulls. If you are holding this and pulling this way, right? My right hand is being pulled by the string. My left hand is also being pulled by the string. I am pulling the string this way. My right hand is pulling this way. My right hand is being pulled to the left. My left hand is being pulled to the right. Here, tension is acting away from my hand. Here, tension is acting away from my hand. Right? If I take any one single point, tension acts away from that point with respect to that point. Always draw the free body diagram separately. Somebody is desperate to consider 5 and 10 kg block as one block and find T2. In this case, you can do, but please don't do it. You have typed that message 3 times. Next time you type that message, I'll remove you from the meeting. You don't understand English. I have told you so many times today not to type messages unnecessarily. अब इतना desperation that you should consider both as one system यार हद हो गई. So T2 you have got as 10G. T1 is 10G. T2 is 15G. This T2 is the tension on that 5 kg block. Find T1, T2 and T3. This is a 5 kg block, 5 kg block and a 10 kg block. I will take the tension in this to be T1, in this to be T2, in this to be T3. Find T1, T2 and T3. When I draw the free body diagram for the first 5 kg block, this will be T1, this will be 5G plus T. The second 5 kg block, I will have T2, 5G plus T3. The third 10 kg block, 10G, T3. They are in equilibrium, they are not accelerating. So T1 will be 5G plus T2. T2 is 5G plus T3. T3 is equal to 10G. Right? This T3, if I substitute here, I will get T2. T2 is 15G. T2 I substitute here, I will get T1, 20G. Wherever you can start, from above or below, we have no problem. This block is not accelerating, so forces in upward direction should be equal to forces in downward direction. This block is also not accelerating. Forces in upward direction should be equal to forces in downward direction. This block is also not accelerating. Forces in upward direction should be equal to forces in downward direction. Now listen, what was your Newton's second law? F external, rather the unbalanced force, balanced force should be equal to mass into acceleration. This is precisely your Newton's second law. So if I take a block of 10 kg and I apply a force of 100 Newton, F will be equal to M into A. 100 Newton is 10 into A. A is 10 meter per second square. Simplest possible thing ever in the history of Newton's laws. F equal to ma. You gave me the force, you gave me the mass, you're asking me the acceleration. So the bottom line is net unbalanced force, you will equate it to mass into acceleration in the direction of the unbalanced force. Now consider this example. You have a 10 kg block here and a 5 kg block here, and you are pulling with a force of 16 Newton. Draw the free body diagram first. This will be T, this will be T. This string is considered to be inextensible. By default, assume that till I tell you. In this chapter, even if I forget to tell you that the string is inextensible, assume it is inextensible till I come to springs. Everything that I am dealing with is inextensible. Second, string is the same, so tension will be the same. Third, with respect to the 5 kg block, tension acts away from it. With respect to the 10 kg block, tension acts away from it. Draw the free body diagram of the 5 kg block. Force is 16 Newton and this will be T. Similarly, 10 kg block, this will be T. Will I not take the 60 Newton on the 10 kg block? No. You are applying that force on the 5 kg block. Draw it only on the 5 kg block. This will be called the free body diagram. Right? Right now we didn't introduce friction, so all surfaces are smooth. Second half of this chapter, we will introduce friction. Till then, assume smooth surfaces only. Now the beauty in the problem is, the string is inextensible. So if this end moves by a distance of x1, this end also moves by a distance of x1. Both the ends will move by the same distance, or by the same velocity, or by the same acceleration. If this is going to the right with an acceleration of a, this will also go to the right by the same acceleration. Right? If this goes to the right with an acceleration of a, this will also move to the right with the same acceleration. Right? So what will be the dynamic equation for this? Net unbalanced force F minus T is 5 into A. F minus T is mass into acceleration. F minus T is mass into acceleration. F minus T is the net unbalanced force, which will be mass into acceleration. This is my first dynamic equation. T is in the backward direction. F and T are not in the same direction. F and T are not in the same direction. If they are in the same direction, I'll add them. If they are in opposite direction, obviously we will subtract. How about this acceleration? T is equal to 10 into A. There is only one horizontal force acting on the 10 kg block. Right? There is only 1 kg, there is only one force acting on the 10 kg block. That T is mass into acceleration. Cancel this out. This is 15A. How much is the force given? 60. I added both the equations. 60 is equal to 15 times A. 4 meter per second square. Acceleration of both the blocks is 4 meter per second square. Right? Net total unbalanced force is mass into acceleration. Net total unbalanced force. This force minus this force is mass into acceleration. Second, these two are two ends of the same string. These two are two ends of the same string. The string cannot be stretched. Length should remain constant. So displacement of both should remain the same. So velocity of both the ends must remain the same. So acceleration of both the ends will remain the same. Right? Now, once I get the acceleration, can I calculate the tension? T will be 10 into 4, 40 Newton. Can you calculate the tension? Put the A here, you get the value of tension. 40 Newton. Is this clear? Take it down till here. Vector sum of all the forces is mass into acceleration. Vector sum. So if the forces are in opposite direction, by default you will subtract. Vector summation of all the forces is mass into acceleration. Vector sum of all the forces is mass into acceleration. 2 kg block, 3 kg block, 5 kg block connected by strings here, and you are pulling with a force of 15 Newton. Find the acceleration and the tension in the strings. Find the acceleration and the tension in the strings. There are two different strings, so you will take T1 in one, T2 in the other. Take tension T1 in this. Take the tension T1 here and T2 here. Draw the directions of tensions properly and draw the free body diagram. On the 5 kg block, T1 will be this way. On the 3 kg block, T1 will be this way. With respect to this point, it will be away from this point. With respect to the 3 kg block, it will be away from the 3 kg block. This will be T2 and this will be T2. This separating the body and drawing all the forces on it is called free body diagram. You're freeing the body from a system and you're showing the forces. F is 15 Newton. This is T1. Why are you not showing me the vertical forces here? I don't need it. I don't need it. Hence, I'm not showing the vertical forces. If not, MG would have been shown. 3 kg block. This will be T1. This will be T2. Tension acts away from a point with respect to that point. This is T2. These two are two ends of the same string, which will not stretch. Length of the string should remain constant. So this and this will have the same acceleration. This and this will have the same acceleration, and the length of the string will be the same. Because the length of the string remains the same, both will have the same acceleration. Now, if this has an acceleration of A and A, net unbalanced force on it is F minus T1 is 5 into A. Net unbalanced force here, T1 minus T2 is 3 into A. Net unbalanced force is equal to mass into acceleration. Third, T2 is equal to 2 into A. Before you ever start solving the equations, remember to verify number of equations and number of variables to be the same. I have 3 equations. How many variables do I have? Acceleration is one variable, T1 is one variable, T2 is one variable. I am adding all the 3 equations. T1 will get cancelled. T2 will get cancelled. F is equal to 5 plus 3 plus 2 into A. What is the value of the force? 15 divided by 10 will be the acceleration. 3 by 2 meter per second square is the acceleration of all 3 blocks. How do I get T2? T2 is 2 into 3 by 2, 3 Newton. How do I get T1? T1 is F minus 5A. F is 15 Newton, right? Incidentally, T1 becomes 0 if I have done the calculation correct. T1 doesn't become 0 here. I have gone wrong somewhere. F minus T1 is, sorry. T1 minus T2 is 3 into A. T2 is 2 into A. Acceleration I have taken wrong, right? F is 15 Newton. What is the acceleration? 3 by 2. Acceleration is 3 by 2. 15 minus 15 by 2. 7.5 Newton is T1. T2 I think I already calculated. T2 I already calculated. T2 is 3 Newton. T1 is 7.5 Newton. System is accelerating towards the right. So forces in that direction minus forces in the other direction. 1 second. Sorry. Yeah. Right. There was a call which came which I had to address. Sorry. Now you are able to hear me? Yes. Okay. Take it down till here. Now, if the body is accelerating this way, I will take all the forces in that direction minus forces in the opposite direction is equal to mass into acceleration. Now somebody is asking, don't you think there will be reaction on the 2 kg block? Here, 2 kg block per T2 is the action. Reaction will not be on the 2 kg block. Action and reaction will never be on the same block. It's like telling you 3 kg block is pulling the 2 kg block, 2 kg block is pulling the 3 kg block. 3 kg block is pulling the 2 kg block in the forward. 2 kg will pull the 3 kg in the backward direction. So action and reaction will never be on the same body. Is it clear till here? The next force we have to introduce is normal force. Pushing. Till now you were seeing only pulling. Now I have to push. Till now you are seeing only pulling. Now we'll have to push, which we will introduce in the next class. See you people in the next class. Good day. Bye. And thank you.